Hello everyone. My name is Parvathy, 12th Sem MSc Ed Physics RIE Mysore. Today I am going to present on the topic bottom up approach in synthesis of nanomaterials. In this presentation, I will briefly introduce nanomaterials, discuss the two major synthesis approaches, and then focus mainly on the bottom up approach, its formation process, techniques, advantages, disadvantages, and applications. And we will conclude by comparing top down and bottom up approach. To begin with, let us understand what nanomaterials are. Nanomaterials are materials that possess at least one dimension in the size range of 1 to 100 nanometers. At this extremely small scale, materials exhibit size dependent properties that are significantly different from their bulk form. So, due to this reason, nanomaterials act as a bridge between atomic scale systems and macroscopic materials and have gained enormous importance in modern science and technology. Here, in this figure, it is the SEM image of TiO2 nanotubes. It is clearly showing the nanoscale dimensions and surface structures of nanomaterials. Now, coming to the synthesis of nanomaterials, there are two main approaches, top-down approach and bottom-up approach. In top-down approach, a bulk material is reduced to the nanoscale by removing material using physical or chemical methods or mechanical methods also. On the other hand, the bottom up approach involves assembling individual atoms, molecules, or clusters to form nanostructures. The diagram shown here clearly illustrates the difference between breaking down bulk materials and building nanomaterials from atomic or molecular levels. Among these two approaches, my presentation mainly focuses on bottom up approach. The bottom up approach is a method in which nanomaterials are constructed starting from the molecular or atomic level. Initially, atoms or molecules come together to form small nuclei. These nuclei then grow and assemble to form nanomaterials. This approach provides excellent control over particle size, shape, and composition, making it highly suitable for synthesizing functional nanomaterials. The schematic diagram shown here represents the gradual formation of nanomaterials starting from the atoms. As you can see, there is molecular or atomic level. Slowly it grows, nuclei and its growth, then nanoparticles are formed. Now, let us understand how nanomaterials are actually formed in the bottom up approach. The birth of nanomaterials takes place through three important stages: nucleation, growth, and stabilization or assembly. During nucleation, small clusters or seeds are formed due to energy input. In the growth stage, these nuclei enlarge as atoms or molecules. They continue to deposit on them, and their size, shape, and crystallinity are controlled by parameters such as temperature and concentration. Finally, during stabilization and assembly, nanoparticles are prevented from agglomerating and controlled organization is achieved, sometimes using templates or surfactants. The image shown here clearly visualizes these three stages, showing how nanoparticles evolve step by step, as you can see. Several techniques are employed in the bottom-up approach. Among them, I will briefly explain only four important techniques. First, chemical vapor deposition. Second, hydrothermal. Third, chemical precipitation. Fourth is the salt gel method. Now, let's move on to chemical vapor deposition, commonly known as CVD. Chemical vapor deposition is a bottom-up technique in which gaseous precursors are introduced into a reaction chamber, as you can see, and allowed to react on a heated substrate. Under controlled condition, what happens? Nucleation and growth occur, resulting in the formation of uniform nanostructured or thin films. The image here illustrates how precursor gases enter the chamber react on the substrate, and deposit nanomaterials. Next, we'll move on to hydrothermal synthesis. In hydrothermal synthesis, precursor solutions are heated in a sealed autoclave at very high temperature and pressure. So, this controlled environment promotes nucleation and crystalline growth of nanoparticles. The diagram shows nanoparticle formation taking place inside a high pressure autoclave, as you can see. Another simple and widely used method is chemical precipitation. In chemical precipitation, nanoparticles are formed through controlled chemical reactions in a solution. Processes such as aging, washing, and drying help in obtaining stable nanoparticles with desired properties. This image shows the stages involved in precipitation and nanoparticle formation. The next technique is salt gel method. In this salt gel method, a precursor solution will undergo hydrolysis and condensation reactions to form a salt, that which later will transform into a gel. So subsequent drying and calcination process result in nanomaterials. Examples are zero gels or aerogels. The image here clearly depicts the transition from salt to gel, and finally you can see a solid nanostructure is formed. Now, let us discuss the advantages of bottom-up approach which make it highly preferred. One of the major advantages, excellent control over particle size and shape. This approach produces nanomaterials with high purity and uniformity while minimizing the material wastage. Additionally, it also enables the synthesis of complex and functional nanostructures, making it suitable for large scale chemical synthesis. The image here shows self assembly of nanoparticles, demonstrating controlled organization at the nanoscale, as you can see. However, bottom up approach also has certain limitations. It is often difficult to control large scale alignment and placement of nanoparticles. So, due to their high surface energy, nanoparticle may agglomerate. Moreover, precise control of reaction conditions is required, and reproducibility can also be sometimes challenging. The TM images shown here clearly indicate the agglomeration of nanoparticles, which makes it little difficult for further applications. Finally, let us look at the applications of nanomaterials synthesized by the bottom-up approach. You can see there are various applications and various images here. In nanoelectronics, they are used in semiconductor nanowires and thin films. Here you can see graphene. In catalysis, metal nanoparticles enhance reaction efficiency due to their large surface area. In biomedical application, nanoparticles are widely used for targeted drug delivery. You can see how the process takes place in this diagram. They are also employed in nanosensors for detecting pesticides and environmental pollutants. So if any fruits, any pesticides are more, we also use nanosensors to detect it. The images shown here represent these diverse and real world application, as you can see here. Before concluding, it is very important to compare the top down and bottom up approach, as both play significant role in the nanomaterial synthesis. As you can see, in the top down approach, we start with a bulk material and reduce it to nanoscale using physical or mechanical process such as cutting, milling, or lithography. This approach is essentially a material removal process. So, while it is compatible with existing microfabrication techniques, it often results in surface defects, material wastage, and limited control over particle size and uniformity. In contrast, as we see, the bottom up approach begins at the atomic or molecular level itself. Atoms or molecules assemble through nucleation and growth to form nanostructures. So, this method provides much better control over size, shape, and composition. As a result, bottom up approaches are more suitable for synthesizing uniform, high quality, and functional nanomaterial. As you can see in the diagram, they clearly highlight the fundamental differences. Here, the top down approach moves from bulk to nano, whereas the bottom up approach builds nanomaterials from the smallest building blocks. When we compare these two approaches from a practical perspective, several important differences can be observed. A detailed table is given here. The top down approach generally involves higher energy consumption and greater material wastage as excess material is removed during processing. It may also introduce contamination from tools and equipments. So, it is easier to integrate with existing industrial fabrication methods, particularly in microelectronics. On the other hand, the bottom up approach is more material efficient and usually produces nanomaterials with high purity and very few defects. So it enables the formation of complex and hierarchical nanostructures which are difficult to achieve using top-down methods. However, there are few challenges such as nanoparticles agglomeration, strict control of reaction condition and reproducibility must be carefully managed. Overall, while both approaches have their advantages and limitations, the bottom up approach is preferred for precise control and advanced nanomaterial applications, whereas the top down approach is useful where large scale patterning and fabrications are required. Considering these comparison, it is clear why the bottom up approach has gained a greater importance in modern nanoscience. Thank you.